Welcome back, physicists. In this video, we are going to go ahead and jump into our final section of Chapter 8, where we have been looking at rotational motion. And today, we will have the second to last or penultimate section, 8.3, where our focus is going to be on the idea of equilibrium. So, remember that we've seen equilibrium before. All it represents is that we have some net force of zero where everything is balanced. And as a little motivation here, we want to make sure that we can analyze through a physical viewpoint how an object in static equilibrium experiences force and torque. So we will start this discussion with the idea of the center of mass. Now, because we are going to be using this so many times today, I'm going to go ahead and use COM with intentional capital letters to shorthand that. So when we think about a center of mass, the easiest way to kind of envision this is if we look at an object that's maybe being thrown. So I throw a pencil and it kind of twirls. There exists a point on that object as it's thrown through the air that behaves as if all I had thrown was that single point. So we'll define this using that idea. We'll say that this is the point on an object whose motion behaves like a point particle. Like a point particle. And if we look at this, there is an image in your text that you'll find on page 219 where they show a wrench being thrown, and you see that there exists a point on that wrench where, as I watch this thing spin as it flies through this picture, I can see there's a single point that just essentially follows a straight line. Now, in application of this, what we can start with, or what we can look at, is how would we actually go about locating a center of mass? Now, if you look back at geometry, there was a section where you looked at centroids, circumcenters, orthocenters, and incenters. And in that lesson back in geometry a couple years ago at this point, what you did when you found the centroid was you found the center of mass for a triangle. Now, oftentimes in our world, it's not that cut and dry, right? We don't have perfect, nice triangles that we can deal with. So if we were trying to find a center of mass for some goofy object, for example, I'm going to draw a cup because it's easy to draw. First thing that we would do is at any point on that object, we would stick a string or a rope, something to it, and suspend the object. Now, after we suspend this, we'll go ahead and add just a little bit, then draw a vertical line from string. Now, I'm not going to write it here, but what we do as we carry this out is if I have some cup, and I'll use a sideways cup here. So let's say I have a cup here, and there it is. It's beautiful. It looks like a nice little drinking cup. If I have this cup, and I'm just envisioning it, and I hung it from a string right here, it would be hanging, the string would be vertical, just due to the nature of how, gravity pulls on things. And I'm going to go ahead and just imagine that that line has been extended. So there's my vertical line. Now, once we do this, all we have to be able to knock out is step 2, do the same from a different point. And I think I changed the green color there, so I'm going to try to see which one I had. Must be that one. That's close enough. Okay, so if we hang this same cup again, and let's say we hang it from a different angle this time, and hypothetically, I'm going to try to hang it. Let's say it's tilting this way this time. And let's say I hung this cup and I tied it right here is where I imagine it would be. We would see, and I want to make this a little bit different of an angle. Let's say that I have this thing a little bit more tilted. And I'm just switching here so I can make sense of it in my head because that direction didn't seem very natural to me. Now, if I hang that same cup, I imagine it would be somewhere like this. And like we did before, I'll go ahead and extend this out. Now, if we could somehow take this line from the first picture and draw it through here, what we would find is something that looks like this. And I'm just going to do it all in this red. This line in that orientation would wind up about right there. And the intersection of these is our center of mass. So we could hang objects and we could find centers of mass. When I return, that seems like something that we might be able to find some time in class to make sense of. Now, like you guys, I care most about, myself. So we better look at just human in general. If we have a human being, what is their center of mass going to look like? Now, typically, and this is just a quick comment, a centimeter or two below a navel. Below the navel. So your belly button, essentially. Now, as a follow-up for this, there are some slight differences that you might see if you've ever seen the TikTok challenges where people, try to pick something up and they wind up falling, whatever the case might be. As you look at this, we'll just say, in general, not always the case, but women typically have a slightly lower center of mass. Okay. So we've looked at how does one find the center of mass? What does it look like on a person? We're not going to hang a rigid person up like this and find their center of mass, I don't think. But we're going to go ahead and take this one step further. So oftentimes we worry about things like center of mass, because we get in these super heavy, fast-moving machines that could cause a crazy amount of damage if we crash them. Our cars are at the mercy of the single idea of center of mass and stability and making sure that those things are always in sync. And as we look at this, cars are an easy example. We don't have to be fancy with our drawings, but we're going to look at our second main topic today, where we'll compare and contrast, I guess not really contrast, but we'll make sense of center of mass and how it impacts stability. So, as we look at something and ask whether it's stable or not, this isn't a really formal definition, hence why I'm not writing it down here. But when we think about something being stable, we're associating it with some amount of force that would be required to tip it over. So, as an easy example of this, we're going to tip a box, and we're at least going to envision tipping a box. Let's tip a box. An odd spacing here, but I'm not going to change it. So, let's say that we have a box, and we're going to draw 3 frames here, and they're all going to be the same box. So here's a lovely box right here, and it looks like a nice rectangle box, so that's fine and dandy. And we'll go ahead and just copy this and paste it a couple times, and we're going to add some forces to this as well. So I'm actually going to take this tool and put it up here because I use it so frequently. And we'll go ahead and knock that out. And there's one. And I don't need to copy and paste it. What am I talking about? All right. So let's say that here's the box. And what I'm going to do is I'm going to put some scribbles here to indicate that this is the base that I'm looking at. So we have this box, theoretically. And let's say we grab on, there's a string or something hooked to it, and we apply a force right here. Now, unless we're working with some crazy sort of magic box, we have a center of mass that is acted on by gravity. So not only do we have a force that we're pulling or pushing on this box, pulling from this perspective, but the box, because it has mass, also gets pulled down by gravity. Now, if I have a rope connected at this point, then I'm going to highlight this guy right here, and you can put it in your notes if you would like, but I'm going to refer to this as our pivot. If I pull the box and it doesn't just slide, that's where it's going to start to tip. And what we're going to see is a couple things. First, if this is the point that I'm hoping to pivot on, this force that I'm applying is going to result in a torque that goes this direction. So we'll go ahead and label that T sub F for the torque that's been caused by this force. Now, because this box isn't going to start rotating unless we pull a little bit harder, we must have some sort of torque that's canceling this out, because otherwise it would be moving. So that only can come from this other force that we have acting on our box in the form of gravity. So we'll go ahead and say, check this out. If I'm trying to make the torque, if I'm applying torque that's turning the box this way but it's not moving, there must be an equal but opposite torque at this point that's caused by gravity that's counteracting me. So similar to the idea of force that we pull and friction, it's rotational force or torque, and the opposite torque due to gravity. Okay, so here's step one. Now, if we start to pull a little bit harder on this box, inevitably we are going to get to a point where it tips, or it begins to tip anyway. So let's say here's a second later, and I have my box now being tipped. And same like we did before, I'm going to scribble that so that it's clearly the base. Now, we have this set up, and I'm trying to wait and stall a little bit so you get time to draw this. But if we continue to apply our force to this thing, we're continuing to apply it, it winds up that I'd be pulling like here at this point, just due to the nature of how this box is turned. So here's the force that we're pulling at. And just like before, we have a torque that's fighting me this direction. And we have the torque caused by that force. And then my center of mass is here, and it's still pushing down. Now, I've drawn this very intentionally because we see that the force of gravity seems to be pushing right through that pivot that we had. Now, in this situation, if it hasn't made the decision yet to tip, then there must still be a torque caused by gravity pushing back right here. Now, what I want you guys to try to do is, if we go one step further, I want you to spend a moment to sketch out, discuss with your neighbors, if we go one step further, meaning that we have our box that's now essentially been tipped over, so let's say it's this guy now, and if I don't apply any more force, it's going to keep going. But let's say I have this. Sorry, I keep holding the keys and it's trying to do something. I don't know. But here's my base all of a sudden. What I want you guys to do is spend just a second, like 30 seconds, talk with your neighbors, decide where are we going to draw our torques and has anything changed about it. So if whoever's running the show up there on the board will pause it, I will go ahead and give you guys just a moment, and when you're ready, resume the video and see if we all come to agreement. Cool. So resume in 3, 2, 1, and here we are. So looking back at this, just to see, we're still applying this force, or we don't have to be, but we may as well, which is producing a torque going in this direction. And I do want to highlight that, just recall that this is in fact a negative torque because it's turning in the clockwise direction. Now, in this situation, something fundamental, or something is fundamentally different. We now have the center of gravity's force due to gravity pushing down, but it's outside of the base, which means I'm now pulling this thing across this pivot like it's been the whole time, but suddenly our torque has shifted. And specifically, at this point, if I let go, this thing is just going to tip. We see that in order to tip something, all we have to do is move that center of mass outside of the base that's trying to support it. So we can summarize that fairly easily. We're just going to say objects are stable, and this is kind of like a follow-up statement here. Objects are stable until, and that's an important part, until our center of gravity, or center of mass rather, until our center of mass no longer hits the base. Now, I'm going to fix this because it sounds funny as I read it. Objects are stable until our center of mass, and I'm going to say just in parentheses, the force due to gravity at this point no longer hits or crosses over the base. So if we stop applying force but our center of mass isn't there, we're going to see that thing tip. Now, I'm trying to go fairly fast through this first little section. If there's any concerns, things that don't quite click, please take a second, check with your neighbor, see if as a class, even though I'm not there, we can maybe try to fix some of these issues. And I'll give us like 10 seconds. If we don't have any issues or things to look at, we're going to go ahead and continue on. So starting now. And we will be picking back up in 3, 2, 1. So as we start looking at this, we've covered the conceptual component of stability and center of mass, but we're going to go ahead and dive in and cover a couple more concepts, one more small concept, and then jump into a problem. So we'll go ahead and call this conditions for equilibrium. Now, as we look at equilibrium, there's really two different flavors that we're going to concern ourselves with. And if we're looking at objects and we're trying to prevent them from moving, then what we're really concerning ourselves with is this idea, and I'm going to sneak this in as a definition, of static equilibrium. All right, so static equilibrium. Now, for this, we're just going to say it's equilibrium where things don't move. And I'm not going to even bother writing it. Static means no movement. Equilibrium means equal forces. Now, before, everything up to now when we've thought about it not moving, what we've really been speaking to is this idea of translational equilibrium. And I'm just going to write translational because equilibrium hopefully is implied. Now, if we relate this to math, then translations are just shifts left or right typically. So if I'm not moving left and I'm not moving right or up or down, then what we're really talking about is just this basic idea where we say, hey, the net force acting is 0 newtons. No force is acting. Now, again, this is for that nice linear world. As we move into our new pieces, we get not only translational equilibrium, but also rotational. And the cool thing about this is it actually is pretty straightforward as long as we can make this connection between force, which is what causes linear motion or linear acceleration, and the thing that causes rotational or angular acceleration. And this is just simply changing our viewpoint. We just see that instead it's the net torque acting on some object winds up as 0 Newton meters. Okay. So have this piece knocked out. We are going to go ahead and jump into a problem, and I'm going to use a little editing magic. And here is the problem that we're going to be looking at for the next several minutes. So if whomever's running the pause and whatnot would go ahead and give everybody time to get this written down, I will go ahead and have you draw this as well. Just to be clear, these are sawhorses where it's what you would put something on like a ladder if you wanted to have it sideways. So go ahead, get this written down. This is our only example, so I didn't bother making a worksheet. and I will resume once everybody has this written down and it's unpaused. So see you in 3, 2, 1. Now, as we look at this problem, we are going to go ahead and jump right in, and we're going to indicate our knowns. So right off the bat, I see that we have a mass of 6.3 kilograms. Okay, so that's the ladder. Now, furthermore, I'm told that the length of this ladder, and I'm going to use an L here, the length of the entire ladder is 2.11 meters. So I have my nice, wonderful picture. I will go ahead and get this set up, and we'll say, check it out. Here's L. And what else do we know? Sawhorse A, so this point at A, is 0.5 meters from the edge of the ladder. So here is 0.5. And just to stay consistent with it and what your book does in case you're using that, I will indicate this length by its length of the ladder from point A until the end. So we know that this is 0.5 meters. Now, I also am told that from B to the end of the ladder is 0.10 meters. I forgot the meter and it's driving me crazy. So we'll go ahead and we'll indicate, hey, the length from B is 0.10 meters. Okay, this is everything that I know at this point in time. So we'll just indicate that, hey, check it out. We have all of our knowns listed. I'm going to find the force that these sawhorses are putting on the ladder. So we're looking for the force of A, and we're looking for the force of B. Now, just to help us make a little bit of sense of this, I think it'll be pretty helpful if we take this picture and we also make sure that we can identify the forces. So here's my ladder. Everything's all the same. And let's just think about the forces that are acting on this. Now, there's a center of mass somewhere on this ladder. And I know that realistically it's probably in the middle as long as we're uniform. So I'm going to indicate that, hey, check it out. Here's a force of gravity pushing or pulling this thing down toward the ground. Some force of gravity. Now, beyond this, I also know that there's a point A and a point B that are resisting gravity. So I'll try to make that a little bit closer. And specifically, what I mean is if gravity is pulling down, then A must be pulling up somehow, and B must be not pulling but pushing up. So here's the force of A and the force of B. All right. 2 of those up and ready to roll. So all of these ideas are going to be working together. And this problem is more complex than any that we've done. And I'm not trying to scare you. I just want you to make sure, be comfortable asking your classmates if there's something that you don't get, or if you need somebody to try to explain something, or if you see a classmate struggling. All of those things are important. So here we go. We're going to start by just recognizing that I need 2 different things, and there's a lot of pieces that are involved in here. But right off the bat, I know that this thing is not moving. It is static. It is being balanced out. So from that, I know that the net force is 0. And I'm going to write this out, and we'll substitute in and just comment. The net force of all the stuff acting on this is simply going to be force at A, force at B, and then it's going to subtract the force of gravity. So it's the force that A pushes up plus the amount that B pushes up minus the amount that gravity pulls us down. Okay. Now, all of our net forces. Going one step further, we also know that because this thing's not moving, this net force is 0 newtons. So one little tiny step, force A plus force B minus force of gravity still. And here we get to make a decision. Now, in this problem, as we approach it, you're going to find that we're essentially going to act as though there's a single pivot and we'll make sense of it from there. And this is an arbitrary choice. Now, to make this as easy as possible so we're all on the same page, we're going to imagine for a pretty big portion of this problem that I'm using point A as my pivot. Now, with that in mind, I'm going to change color and I'm going to indicate something. I could solve this equation for the force of A. So I'm going to indicate that, hey, this is going to be equation 1. I think we're going to use it later. But rearranging this equation, we can obtain that the force of A is just going to be the force of gravity minus the force at B. So I've rearranged, and I know it feels weird, but I just added Fg and subtracted F Bravo. Now, I'm going to make one comment here just so we can see it. If we just somehow had a way to find Fb, we would be golden, because the force of gravity is just mass times gravity, or ma, mg, however you want to write it. We simply need Fb. So this is now the kind of way to work through this. Now, this is back to that comment just a moment ago where we talked about we're going to think about this thing spinning about point A. If this right here is my pivot point, then about point A, I would have B, this force, producing a torque this direction. So this is the torque caused at point B. Now, in contrast with that, if we were trying to look at gravity, it would be rotating about this point and pushing downward. So we would see that going the exact opposite direction is the torque that's caused by gravity. So they're counteracting each other. We have zero net torque, so they're both undoing each other. So we're going to jump in and we're going to use that net torque idea. So here we go, T net. And I'm going to change the notation just a little bit. I know that overall there is no net torque. None. It's zero. Now, specifically, I also know that in this system, if we're pivoting around A, because we're setting up that way, then the two torques that I would have to be dealing with would be torque B and torque G. So 0 must just be the torque caused by gravity plus the torque caused at point B. Nothing crazy happens, with one little exception. So here we go. I know that if I rearrange just this part, so don't erase yours, but I'm just rearranging this, we can then obtain that the torque at point B, or caused by force at B, is equal to the negative torque of gravity. Or it doesn't, maybe it's easier to think about, if I just subtracted this, I would get the negative torque at B is equal to the torque of gravity. And honestly, I like this idea. And the reason that I like this idea is that when we look at this, at B, and I lied, I like this idea more. It'll work either way, but this one I think is going to be easier to just kind of make sense of. Now, what I see here is B is a positive torque because we're going counterclockwise, and G is a negative. So to straighten things out and make this just a hair easier, well, I think that we could probably get by with saying that the torque at B is negative the torque of gravity, which was already a negative. So we may as well just get rid of the negatives and simplify this. Torque caused at B and G are equal because one of them is negative direction. Okay. Now, this allows us to go one step further. And I just want to remind you, we were trying to solve for force B somehow. And it turns out that maybe, just maybe, it's going to show up here. If I want to find the torque at point Bravo, then I know that torque is the force at Bravo times the radius of that point from the axis that we're rotating around, or RB. And that is exactly equal, according to our previous line, the force of gravity times the radius from the center of gravity to what we're rotating around. So I'm going to go ahead and add one more little thing here. Remember, this is our pivot. So as we're trying to make sense of all these ideas, what I recognize is that this distance, whatever it is the distance from our force to our axis. And then the larger distance from here all the way over to here happens to be the radius at point Bravo. So I have a way to look at these and think about them. We're going to go one more step, and I'm going to make this one blue. And I'm going to call this equation 2. And rearranging this, I think it's reasonable to say, hey, the force at B, it turns out, is just the force at G, times RG over the radius of Bravo. I'm going to start using golf for G as in golf. Cool. So all of a sudden, notice we had an equation here that had 2 unknowns, and I have an equation here that solved for one of those unknowns. So let's do a little system stuff and put red and blue together. And I'm not great at this, but I'm pretty sure that these things together are going to make purple. So we'll go ahead and do this, and we'll switch to a lovely purple color. I think that's purple. And we'll do the following. I can now rewrite the force of A. And we'll go ahead and say that, hey, by using this substitution, the force at A is just the force of gravity minus, and instead of writing this FB, I'm going to write this one since we just found out what it's equal to. So here we go. Force of gravity, radius of gravity over the radius of Bravo. Okay, we have an awesome expression here. I am going to ask that you guys pause this at least momentarily, and I'm going to give you some time to work, but I'll put a little guidance here. With your tables, with your neighbors, whomever you have near you, I want you guys to see if you can't find a few things for me. So this will be the last little few comments of the video. The next ones that you see, you will find them, you will just see the whole problem worked out. But what I want you guys to do is sub what you know or can find for FG, RG, and RB. Now, further little push, I'm not sure you guys need it, but remember that force is just mass times gravity. So, plugging in for these things on the right side of this equation, I want you guys working together to see if we can't get a number out of this for the force of A. So our work might look a little different. I'll talk through it at least a little bit once it's complete, but please somebody go pause the video and you will see all the solution. So make sure it's paused in 5, 4, 3, 2, and 1. So here is my work for force A. Half the problem, or way more than half the problem realistically. And as you're looking, I kind of assume that you guys plugged in numbers at this point in the problem, but I went a step further because I don't want to plug stuff in until I have to. I factored out mass times gravity, or the force of gravity, from each of these. I simplified it. I plugged in. I played the unit game to ensure that my answer was correct. And the part that I want to make sure that we can hit, and if you struggled, my hope is that somebody in class was able to discuss it with you, is these numbers, the radius of gravity and the radius from point B. So as we look at this, I left a little bit blank, but I left it blank very intentionally. And I'm going to scroll up to look at this picture. I know that this whole distance L was 2.11 meters. And in turn then, that means this middle section from A to B was 1.51 meters. And that's a very terrible choice of that. So I'm going to make that very clearly a 1.51. I hate it. But as we look at this, we get to, or have to rather, assume that our center, as long as it's uniform and not crazy, our center of mass is going to be right in the middle. And we just need to be able to calculate this value. Now, to do so, all that we wind up doing is take the whole length and cut it in half, but we take only this little distance right here. And am I goofed up here on this? So, and I'm sorry, I got caught up looking at it. As I calculate it, I wind up taking, and I'm going to show the work here just in case, I need 1/2 the length. So that would be this average point right here, right in the middle. But then I need to take off this distance. So that's my bad. So we take the average of this, so 1/2 of the length, which winds up giving me that 1.055. And then we just simply subtract this off. Sorry, I had a little brain hiccup there. My mistake. All right. So here we are. We now have force A. We've identified how hard this has to push up. And we have a couple options. We could restart essentially the entire problem and then just act like point B or A was our pivot and switch it around. Or, just hear me out, or we can use 1 right here and get from this our force B. Or, again, just hear me out, because we have so many options, we could use this equation right here. And I think that's the easiest way to go. So I'm going to do some scratch work right underneath. At B, all I need to be able to identify is the radius, the force of gravity. So here's my mass times gravity, times the radius from the gravitational center, which is 0.56, or r sub golf. And we just simply divide by r sub b. And we have all these numbers. And all of a sudden, we can then conclude, and I want you to verify this, we get about 23 newtons of force here. Cool. Now, this problem is long, and I get that, totally understand. There is another very similar example in your text that you can find on page 222, where they do very similar thing. I speak about it a little bit differently. But with the time that we have left, what I want you guys to do is begin working through homework 8.3.1 that you will find on page 223. Now, on this page, I want you guys to work through problems 38 through 41. And here's the part that I want you to be mindful of. There's a possibility that you did not have much time left to work on in class. I recognize the challenge of some of this stuff. We can try to get together or have me zoom into a class some point this week. But at the end of the week, I will have a place for you guys in Google Classroom to go ahead and take a photo of this and submit it to the appropriate assignment in Google Classroom. Now, I want to see evidence that you're working on stuff. If you have questions about it, you might not have full answers for every single question, but I do want to see that you guys have tried. Same thing, same rule as always. I want us to commit 30 to 40 minutes outside of class working on this. By Friday at 11:59 p.m., I want you to take a picture of this on your phone, upload it to the assignment on Google Classroom. All right. Well, I will see you guys in our next video, and hopefully you found this helpful. Please do not hesitate to reach out by email if you have any thoughts, concerns, issues with it. And just as a quick reminder, you can reach me at kholloway at, you guys know the address because this is going on YouTube and I'm not going to finish the rest of it. So I'll see y'all in the next video. Good luck, travelers, and have a nice day.